What's going on, everybody? This is the walkthrough video for color differences and review. So this originally started with the color of light 1.3 read about, and we have three questions. The colors that make up white light, and what happens if you take all the colors of the prism and put them back together. So this goes back to a McGraw-Hill section that discusses this. So these are all the actual colors that are within white light. And then we go in to discover how, when we separate them, they spread out. So here's all your colors: red, orange, yellow, green, blue, indigo, and violet. And if you take all these colors and you have some sort of a lens that will concentrate them, you'll get white light. Or if you were to take all these different colors of light and put them into the same area, you'll get white light. There is a, all these questions have already been answered, but it's just a quick overview. Who is Roy G. Biv? So as you can see on the McGraw-Hill, going from the lowest to highest frequency, we have a mnemonic R-O-Y for Roy, G, and then B-I-V, Roy G. Biv. And it's just a way to remember those in a sequence. Going to this website will yield you the data on this results. So I'll walk through how to find that, and then we'll run through these bottom three questions. So we have different wavelengths, and each wavelength corresponds with a different color. And then we have different angles of refractions. The speed inside the glass changes slightly, and then the index of refraction, or just kind of the way that it shines. So we have our laser here with all of our different colors. And we can do this as a ray, or like kind of like a laser beam, or wave. I'm going to be showing you the wave aspect of this. If we line up our tools, so this will actually measure the light, and then we can actually change this material here and then this material down here. And right now we have it on glass, but we can change it to like water and air if we wanted to kind of like experiment how that changes speed. So when we shine it, we can see, and this animation does a fantastic job of actually showing you these waves. And then if you actually move to the other side of the spectrum quickly, you can see that those waves actually do change distance. They actually do change frequency, and it does show that. You can see here, and as I move here, you can actually see the distances between these stretch out. So that's a pretty cool, kind of neat little part of the animation they showed you to like demonstrate that. So this shows you the different speed of the different wavelengths. And if we click on angles down here, this will show you how that wavelength changes as we change colors. And the trend that we start seeing is the higher the frequency, or going back to the McGraw-Hill, the smaller this is, the more it bends. So the smaller that is, the more it bends. You know, this is a smaller angle, which indicates it's kind of bending inward more. So that is a quick overview of how all of this data is gathered. So again, you have the speed. I'll go through it sequentially. You have the color. The angle of refraction is this angle right here. So it starts at 20.1 and it goes all the way to 27.8, maybe 27.9, 27.8. And then the speed of light in glass changes slightly. The speed of light in the air, same. The speed of light in this air, it's always going to be 1. It's always going to be pretty consistent. So after we, and then the index refraction. And this shows you how the speed changes as it's going through the glass. The index refraction is right here. So it starts out at 15, I believe, or 1.5, and then it actually changes and goes up. So describe some of the patterns that you see in the data. We can see that as the wavelength changes, the color changes, the angle of refraction decreases, the speed of light in the glass also decreases, but the index of refraction increases. So all of them except for this one that is highlighted in green, all decrease. So what happens to the angle of refraction as a wavelength decreases? As the wavelength goes down, we see these numbers increase. And then on the next part, we have just a pretty quick video, and it's going to give you some of these answers. I will not be playing the video, but it will ask you the color with the lowest and highest frequency. You can even look at the McGraw-Hill with the low frequency and the high frequency. When we look at the angle of incidence and the angle of reflection, they're always identical. So if the angle is 30 degrees, the angle of reflection will be 30 degrees. In this case, it is 45.6, which is going to be that same angle of reflection. The video does go into a little bit of length that we talked about at the beginning of the unit, where we talk about colors that are absorbed and colors that are reflected. So the color that something is the color that it reflects. So leaves absorb all colors except for green, which means that the color of a green leaf would be green because that's the color it reflects. And then two mediums that slow down the speed of light. Those are obviously two things that we see here. Water and glass. Those will slow down. If we go to air, notice we have a 45-degree angle, and it does not slow it down. It does not have a angle of refraction because it does not bend. The video with all these answers can be found right here. Go ahead and watch it. It is with Professor Dave. And then the color math is in there about the 7 or 8 minute mark. And you can just find those. But again, those are just an extension. Extensions are just exactly what it sounds like. It's people looking for a little bit more enrichment. And in case you miss like a question here, this will help you, that extension credit will help you recover some of those points if you made a mistake. So that's the point of the extension, just to give you a little bit of padding. That's about it. Thanks for watching this video, making an effort. Make sure you get this done, turn this in, and have a good day. Hope you learned something. See ya.